Good morning and welcome to the third session of machine learning in plain English. Like my previous session, this session will not include any math or any programming statements or constructs. So before we get started in the third session, I would like to do a quick recap of what we did in the part 2 of machine learning in plain English. So I started with KNN regression and KNN classification. KNN stands for k nearest neighbors. In KNN regression, we choose some value of k, let's say 3, and then which specifies the number of neighbors. So for every point, it will pick the 3 closest neighbors, and then for regression, it will just compute the average of all the 3 points, and that will be the estimated point. And it will keep doing that for every 3 closest neighbors. In KNN classification, similarly, we specify the value of k, and depending upon the value of k, it will choose the number of neighbors, and based on a majority vote, it will predict the output class or the response class. KNN is a very powerful technique, and k can take any value from 1 up to maybe 50 or something, though optimal values typically are in the range of 5 to 10. And a value close to 1, the k nearest KNN model will tend to overfit, and for larger values it will tend to underfit, so we have to choose an optimal value of k. Then we looked at cross-validation techniques. Cross-validation techniques typically help us to come up with a more reliable estimate of the modeling error, since if we just have a single training set and a holdout set in the proportion of 70 to 30%, what typically happens is when you train the model, and you may actually get a good performance on your test model, but if you take a random sample from your population, it is likely that the model may not perform well. So we need to find a way to have a more reliable estimate of this. So the two techniques, one is leave out one cross validation, the other one is k-fold cross validation. In leave out one cross validation, what we tend to do is we split the data set into n-1 training set, and the last nth will be your test set. So we will train on n-1 and test it on the nth data set, and then we'll do this for all possible n combinations of this. And for each of these models, we will compute the error and then take the average of the error. So since we are doing it for all possible combinations, the estimated error will be a very reliable estimate. The other one is k-fold cross validation, where we partition the data set into k folds or k partitions, and we train the model on k-1 partitions and test it on the kth partition. Again, for each of these tests, we will compute the error and average the error, which error I mean the mean squared error or the accuracy, and hence you will have a much better estimate of what we can expect how the model to perform on any random set. Then we looked at feature selection techniques. Typically in a machine learning problem, it is likely that you will have a very high number of features. Features are the input variables or independent variables, which can run into the order of thousands or even 10,000. So you would want to eliminate those that are not very important. And there are a couple of techniques. So best fit does an exhaustive search of the features of all the features or the input variables, and takes all possible combinations and computes a statistical measure. The key statistical measures that are used are adjusted R squared, CP, BIC and AIC. You can look up what these mean, and picks up the best model based on these statistical measure. Forward fit starts with the null model, and every step it will add one more feature. In the first step it will create n different models for the n different features, and estimate the statistical quality of each model and pick the best model. It's a greedy algorithm. Then it will add the next feature to this particular selected feature, and again compute the statistical measure and pick the best 2-feature model, and then it will keep going on till it gets the best model. Backward fit, what it does is it will take all features, start with all the features, keep dropping one of the features, and compute the statistical measure, adjusted R squared, mallow CP, BIC or AIC, and then drop the worst model, and then it will keep going backward till it gets the best model. And finally we have ridge regression, lasso regression, which does this feature selection automatically. They have the ridge regression is also known as L2 regularization, and lasso regression is called as L1 regularization. These models tend to penalize the weight coefficients for the different features. So if a feature does not have much influence on the output or the response variable, then it will be penalized more and it will have a smaller weight. While ridge regression will make the weights close to zero but not make them zero, lasso regression will actually make the weights of those that are not important as zero. However, I think ridge regression is more popular than lasso. Now let's go to our third session. In this session I'll be touching about support vector machines, splines, that is B-splines, decision trees, random forests, gradient boosting, and unsupervised learning. In unsupervised learning we touch upon principal component analysis and k-means. Support vector machines. Support vector machines come into the class of non-parametric models, and they can be used for both for classification and regression. Non-parametric model, I mean that in our what we saw so far, that is linear regression, multivariate regression, logistic regression, we modeled the set of input features by a single equation. Our estimated function is a single equation of all the parameters, and whereas SVMs do not take that approach. It's a non-parametric model, and it's very, very powerful. And we have linearized SVMs, and they, which can generate linear boundaries between classes with the maximum margin. And we also have something known as SVMs with radial basis functions, which can actually generate nonlinear functions. So for example, in this example here we have two classes. Let us assume that this red stars are one class and this blue triangles are one class. If we tend to use our regular logistic regression, what will happen is it may come up with a boundary like this blue line, or it can come up with a boundary like this red line. Okay, even though they separate, it's not a clean separation. However, if you use SVMs, it will come up with this black line as your boundary, and it will have these what these two blue lines, dotted lines, are called as the margins. So it will try to create a boundary where the margin, that is the distance between the two classes, are maximum. So in that way, SVMs are much more robust in the classification boundary. Okay, so SVMs can generate these kind of linear boundaries, but what makes them more attractive is the fact that they can also generate non-linear boundaries. And the way they do that is they can create complex boundaries, and the way they do that is they transform the input input data space into a higher dimension, and in this transformed space they can you can create a linear hyperplane to actually segregate the two classes. So while this may all sound a little, kind of very technical, I will come up with two examples which will actually make the concept a little easier. So if you look at this last statement, supervised support vector machine is a supervised binary classification algorithm which actually generates n-1 dimensional hyperplane to separate points in an n-dimensional space, okay, into two groups. So for example, the earlier example which we saw was a pretty straightforward example. You could see that you could actually create a very simple linear boundary to separate the two classes. Whereas if I take this slightly more complex example where this red star is one class and this triangle is another class, there is no way I can actually have a linear boundary that can actually separate these two classes. And The way support vector machine does this, it employs a trick, what is known as the radius. It employs a kernel, um, and what this kernel does is it will transform this input space into a higher dimension. So this is a one-dimensional space into a two-dimensional space where the y coordinate is the square of the x value. So if I just transform this input space into another space where I take the square of the xi's and I actually plot it, so I will this blue triangles will come here, and since these are further down, the square will be a little higher, it will go up, and these triangles will, since it's negative and it will be squared again, it will go up. So now in this transformed space we can actually draw a linear boundary. So in this, from a one-dimensional space we moved into a two-dimensional space, and we can create a boundary with the n-1 hyperplane. By that, which means a one-dimensional line, we can separate this two-dimensional space of points. Now let's take a slightly more complex, okay, and then if we transform this 2D space back to 1D, that is, you take this and you actually try and transform it back into 1D, you will find that you actually get this parabolic curve which separates these two set of points. Incidentally, this example was taken from the applied machine learning in Python by University of Michigan in Coursera, and I thought this example is explains it very well. Here's another example, which again you can find some good demos of this on YouTube also. Assuming that we have two classes, here this red stars is one class and the blue triangles are another class. Again, there is no we cannot, it's not a very simple linear boundary. How do we segregate these two classes? What SVM does is, again using the kernel trick, it will again transform this two-dimensional figure with x and y coordinates into three-dimensional. Just move it up. So we'll create a new coordinate, z is equal to x squared plus y squared, which will result in all this x's falling on a kind of you can say a cross section of a cone, and again the red stars will again form in a cross section of a cone. And in this transformed 3D space, we can see that we can very easily have a plane, that is a 2D plane, that is a plane hyperplane, 2D hyperplane, which can separate this two set of classes. So this is the trick that SVM employs while trying to segregate classes, and it's very powerful. And in fact, we can also use SVMs to in multi-class classification. Now let us come to another non-parametric method of regression, which is the splines. It's also another powerful method, and it can be used both for continuous regression or logistic regression. And the way splines work is that sometimes we may have data where it is not possible to just create a simple equation that will satisfy the entire section of the data. So what we do in splines is we divide the data into sections, and we fit either piecewise I mean separate for each of these sections is fit regression line, that is called piecewise constant functions or piecewise linear functions, or maybe you could take a piecewise quadratic or a cubic or a fourth order polynomial. So you fit regression curves for different sections of the data. So, and cubic splines is one such technique that is done, and I will here let us look at this example here. This is the same example which I used in my first session. You have age and salary, and these are data points. Of course, this is a slightly contrived example. in any case, I assume that I cannot fit a single a polynomial curve through all the points. So what I'm going to do is I'm going to take three sections. One section from here to here, another section from here to here, and a third section from here to here. And I'm going to fit polynomial curves for each of this. So actually we have cubic splines actually fit these third degree equations into each of these, and you get a smooth curve in each of these sections. However, if you notice where we created these separate sections, it is not very smooth, and you can actually see that there is a discontinuity. You can see that it's quite ugly and it's not smooth, and this is actually not actually very useful. So there is a method to actually avoid this, and the way they do that is to use what is known as natural and smoothing splines. So in the natural and smoothing splines, you do not need to actually specify these knots where you need to the number of sections that you need to create. This is done automatically, and you have certain parameters how you can specify it. And the way the natural and smoothing splines avoid these discontinuities at these sections is that they are continuous. Since you are choosing cubic splines, that is a third degree equation, typically a third degree equation is continuous, the second derivative is continuous. So typically by ensuring the second degree of the second derivative is continuous for the cubic spline, we make sure that the entire regression line that we get for each of these sections, they all seem to appear to follow a smooth line. Okay, so this is how it will appear. Even though it is doing it in separate sections, it looks like one continuous curve, and it will provide a much better fit for complex data sets where you cannot fit the entire data set using a single normal multivariate regression. Okay, so splines are extremely useful and very powerful. And the next model that I would like to discuss is the generalized additive models. What the generalized additive model does is, for each of the features, that is for each of the independent variables, or each you can choose a couple of them, or in any order that you want. For each of the independent variables or each of the independent features, you can assign you can use a separate model. So you can have maybe a univariate regression for this. You can have maybe SVMs for this. You can use KNN for this feature, and so on, and estimate the final feature. This is another powerful technique that that has been employed in machine learning, and you have certain functions available in R which can do this. Now let us look at the next set of machine learning models. This decision tree. Decision tree is again a non-parametric supervised learning model. So it is again another very interesting technique and a pretty powerful. Decision tree creates a model that predicts the value of the target while it learns simple decision rules. By from the data itself, we can learn a simple rule. So let us look at an example of how it does this. So for example, let us assume we have this age and loan example which we saw before, and we want to classify this. We want to let us say stratify this particular data set. How will we do that? Here these red stars are your loan defaulters, and the blue triangles are paid. So for age and the amount of loan taken can be determined what at which age and which loan amount would they default. So what the decision tree will do is, it will first create a boundary like this. So we can see most of the loan defaulters on the right hand side, so we'll create a boundary like this, and most of these people on this side of less than 35 have paid, and then it'll create another boundary like this. So you can see that above the age of 35 and above when you take a loan of greater than 5 lakhs, then there is a typical loan default. Or you can say, in other words, people who have taken less than 35 or less than 35 years old and who have taken less than 5 lakhs have not defaulted and have generally paid. Okay, so we can create a decision tree like this. If age is less than 35, the loan is paid. And similarly, if the loan is less than 5 lakh, it is paid. For greater than 5 lakh rupees, you have a loan default. So this is the technique that decision tree uses. Okay, the key advantages of decision trees are very easy to interrupt because you get a nice kind of a decision tree where you can actually follow how the decisions have been made and how the classifications are being done. What are the conditions on which it is doing? Unlike some of the other models where you can see the end result, you have some weight coefficients, but you do not know on what basis exactly this classification of boundary is being done. But decision trees have a problem that they can tend to overfit. They can, you can get a very high accuracy, but they may not generalize well. And decision trees, you start with nodes, and then it can keep going on till the very end. That is where which is called the leaf, to a fair amount of depth. And there is a need to prune the tree and limit the depth so that you get a much better performance. And once you build the decision tree for classification, you can use your measures like accuracy, precision, and recall, and compute the performance of the tree. Since we came across the fact that decision trees tend to overfit, and we have the next set of machine learning models, which is the random forest. What the random forest does is it creates a ensemble of trees, or ensemble is just a fancy way of saying that we create a multitude of decision trees, and the random forest also selects a random set of features at each step. So it creates a multitude of trees with a random set of features. So for example, if you had 100 features in your data set, maybe one decision tree will have about 40 features, another will have maybe 35 features, and the third will have 70 features. So based on a random set of features, it'll create separate decision trees, and then what it will do is to classify objects. When you're trying to classify a new object, you input the new input vector, and for all the trees you get a resulting class. And what you tend to do, what the random forest will do is it will pick the highest vote from all the decision trees, and that will be the class that will be output. In the case of regression, you have a multitude of trees. You have an input data point, and when you're trying to predict some value, it will input this data set into your all the individual trees, and then average out the results. Random forests prevent overfitting and usually give excellent results. Another method used in is an extension of this random forest and decision trees is boosting. Boosting, what it does is, instead of just it also uses an ensemble of trees, but they don't create multitude of trees with a random set of features. Rather, you create a small set of features, then compute the error, and then you will the gradient boost will try to improve on each successive tree, and will try to minimize the error. So gradient boosting generally gives much better results than even random forests. Okay, so far all that we have seen, like for example, your univariate regression, multivariate regression, polynomial regression, logistic regression, KNN, SVMs, random forest, decision trees, gradient boosting, all these are all supervised learning. Supervised learning is when you have a set of input data of features and a corresponding output variable or response or outcome. That is, you have labeled data. You know what the input set of features correspond to some specific output response or variable. In unsupervised learning, we don't have that luxury. We just have a lot of data and we need to identify how to handle this. So there are a couple of techniques. One is the principal component analysis, which is used in unsupervised learning. So principal component analysis is used to reduce the dimensionality of the data. So for example, when we have data, we will have a large number of features, right? We may have 100 features, 200 features, or maybe any number of features. And in general, we cannot really visualize the data, what is happening. However, if you would like to explore the data before we do any sort of analysis on it, it is necessary to be able to bring the dimension of that data from maybe 100 to either 2 or 3 dimensions, which can be plotted, and we can visualize if there are any clusters or if there are any how the data looks like. And principal component analysis is a technique that is used to reduce the dimensionality of the data in order to visualize the data better. So when you have some n-dimensional data, n-dimensional or n-features data, the first, you can reduce it into any k components. You can have 1, 2, 3 up to k components, and the first principal component is a linear combination of the features. I mean, it's just a combination of the features in the direction which has the maximum variance. The second principal component is again another combination of features which is uncorrelated to the first principal component, which has the largest variance, and so on. So you can go up to, for n different features, you can go up to k principal components. So let us look at this earlier example of this age and salary. Assuming here this is a two-dimensional data. Again, this is a somewhat contrived toy example just to make things clear. So we have this distribution of data of the salary with respect to the age. So what principle, assuming that we just want to reduce this two-dimensional graph into a single dimensional graph, what we do is we reduce it into the first of two principal components. The first principal component is in this direction because the maximum variation of the data is in this direction. So this is the first principal component. So you draw a line in this direction, and you will draw perpendiculars from these data points to this. Remember that when we did the mean squared error, we took the perpendicular, the y distance from here to this point. Here we take the actual perpendicular from this point to this, and what we do is and the second principal component is perpendicular to the first principal component. Now we actually project all these points onto this red line, and this is what we will get. So essentially what we will get is we will get all of that projected onto this single one-dimensional point, which will be a first principal component, which will enable you to visualize things a little better. So in this contrived example, it is very simple, but typically what happens is when we tend to have hundreds of 200 features, when you reduce it to one or two components, you can actually tend to see a pattern of how the data is distributed amongst all the features, and you can make some initial good decisions on how to handle the data. Okay, now the last and final approach in unsupervised learning is the k-means clustering. As I said, in unsupervised learning, we do not have labeled data. So can we identify patterns? Can we identify clusters in the data set? And the technique that is used is known as the k-means clustering. And the approach is, we initially assume that the data has k clusters. K can be 3 or 4 or 5. You can choose any number of clusters. And then we initially randomly choose the center of these clusters. When I say center or centroid, it means the same thing. Then what the algorithm will do is, it will first find all the points that are close to these centroids, and then compute a new centroid which is the mean of these three selected points, and then it will keep continuing iterating through this process. So I will show this diagrammatically what happens here. Let us assume you have these set of data points, and you want to find two clusters from this. Clearly you can see there's a cluster here, there's a cluster here, but how do we have a machine do this? What will happen is, in step 1, I will randomly assign two centroids, centroid 1 here, the green centroid, and centroid 2, the blue centroid, and this centroid is closest to these 3 points, so I've also colored this in green, and this centroid is blue, so I've colored all these stars as blue. And what this centroid will do is, I will take the mean of these 3 points, which will be somewhere here, and this blue for this blue centroid, I'll compute the new mean of new position where the centroid will move, and it will be here, which will be the mean of these 3 points. So next I move this blue to this point and this green to this point, which is shown here. Now the closest 3 stars to this green point are these 3 stars, and the closest stars to this blue point are these 3 stars. Now I compute the new mean for these 3 stars, which will be here, and the new mean for these 3 stars will be here. So it will finally move to this position. From here, this mean will not move much because we have already arrived at the centroid. Okay, so this is how a k-means approach is done, and it is very useful in identifying the separate clusters that are there in the data, so you can find patterns in the data. Okay, so this concludes all the 3 sessions of machine learning. And as I said, machine learning is not curve fitting. We're not doing service fitting. We're not trying to find the best fit to all the data points. Similarly, we are not just trying to optimize. Machine learning essentially requires our model to be able to generalize well to new data. Okay, that is where the key feature of machine learning is. So this is what I call the machine learning, the Goldilocks principle. In machine learning, the challenge is not just to create a model. That typically can be done using any one of the different models. So you could use multivariate regression, you could use SVMs, you could use KNN, you could use decision trees, random forests, and so on. So you have lots and lots of models to use, and you can tune them. But the key aspect of your model is it should be able to generalize well on unseen data from the same population. So this is exactly what the Goldilocks. So Goldilocks, if you remember that little fairy tale, Goldilocks felt the father's soup was too hot and the mother's soup was too cold, whereas the baby bear's soup was just right. Similarly, the father's bed was too long and the mother's bed was too wide, and the baby bear's bed was just right for it. So machine learning should neither underfit nor overfit. It should fit. You should get to just the right fit, and that's where the challenge and the real what do you say, caliber and good machine learning experts lie in. So with that, I would like to conclude all the machine learning sessions in plain English, and I hope that these sessions have given you some at least a basic overview of the different machine learning models and how they operate, the different measures and the metrics. And I also sincerely hope that they have created an interest in you to further explore this fascinating domain. It's an interesting area where you get to actually think logically and come up with the best possible answer. And I also find it very fascinating that what appears seems somewhat intuitive to us, we can actually make a computer or a program to actually come to the same conclusion. In fact, there are programs which actually perform better than even humans sometimes, deep neural networks. So with that, I would like to thank you for listening and appreciate your time spent on this. Thanks.